Okay, so this video is going to take a look at the integral test, and either the P series test, or I'll make a second video for that. But the first thing you want to do is well, don't look at this answer, right? Pause. I want you to complete that warm up, and make sure you can do that telescoping sequence. And again, just knowing that my denominator is quadratic, right? So the fact that the denominator is quadratic is telling me the terms are going to get small enough fast enough. And so we just have to use partial fractions to sum that up to the finite value of 1.5. So we should definitely feel comfortable when we recognize a not only geometric series, but also a telescoping series where we can sum it up with partial fractions. Now, there are other series that will give us terms that get small enough fast enough, but we don't know how to add them all up. And so we're going to have to rely on tests that basically just verify, yes, it converges, right? It'll give you some value. We might not be able to find that though. And the first test that we're going to get to allow us to do this outside of like knowing a geometric series um, or a telescoping series is what's called the integral test. And so for an integral test, if you have a series that has three conditions, your terms have to be positive. Oops, I didn't mean to cross that out. Sorry. Your terms have to be positive. You have to be looking at a continuous function, and the end behavior has to be decreasing. So if all three things are met, then the series that you're trying to analyze and the integral that represents it as a function, as an improper integral, but still as an integral, will behave the same. So they either both converge or both diverge. We really won't know how to sum up the actual series. We won't know how to do that. But if we represent it as an integral where the series, where the sequence is written as a function, we will be able to integrate the function. And the behavior of that integral will be the same as the behavior of the series. Now, it's not going to tell us what the actual sum is. It's just going to tell us the behavior. So we should make that note. Okay, so let's look at these first two examples. So, again, I'm looking at example one. It's not geometric. It's not, it's not a telescoping series, but I want to be able to somehow determine its behavior. So I'm going to try the only other thing I know so far, integral test. And again, it should be noted that the nth term test won't work because if I look at the limit as n goes to infinity of just the terms, these terms definitely go to zero. So the nth term test is inconclusive. I just wanted to review that. So what I'm going to look at is I'm going to redefine this as a function f of x is equal to 1 over x times ln x. And I'm going to make a note. First of all, f of x is positive. I know that f of x is continuous on the given interval starting at 2. And that the terms are decreasing. So because I've met all three conditions, I know I can apply the integral test. So the integral test applies. Now I realize I'm borrowing space for example B here, so we'll have to go back. I'll have to erase that, and that's fine. So I'm going to use the integral test. So instead of thinking about the series, I'm going to convert it to the improper integral from 2 to infinity of 1 over x ln x dx. Okay? And I'm going to temporarily ignore the improperness of this integral to just actually find its antiderivative. So let's just focus first on doing the antiderivative of 2. Oh, sorry, I just I just even said that. Let's ignore it. So there we go. Just the antiderivative of 1 over x ln of x. Now, it's not too bad of an integral. Let's do a u substitution. Let's let u equal ln x. Oh, I'm getting close to the bottom. I wonder if the pen doesn't work as well. Let's try that again. Erase this. Let's let u equal ln x. So its derivative is sneakily sitting there as 1 over x dx. Right? So we're basically integrating 1 over u du. which is natural log of the absolute value of u. Normally I'd say plus c, but we're going to put our bounds back in. So it's the natural log of the natural log of x when evaluated from our lower limit of 2 to the upper limit of b. Remember, this was an improper integral, so the limit as b goes to infinity. So then that's the limit as b goes to infinity of the natural log of the natural log of b minus natural log of the natural log of 2. Now, the natural log of 2 is just some constant, but what concerns me is right here. As b goes to infinity, well, natural log of infinity gets slowed down, and natural log of that gets slowed down, but it's still infinity, right? This is infinity. The integral diverges. So the fact that the integral diverges tells me that the series will also diverge by the integral test. Because remember, we said we met the conditions for the integral test. So if the integral that represents the series diverges, then the series also will diverge. So I'd want to make a conclusion here, saying, okay, so thus, since the integral, we could say of f of n diverges. And notice I'm being kind of liberal with my notation. I'm just saying since the integral f of n diverges, then the series a sub n, remember we let that function equal that, so it's fine, also diverges. Oop, I'm running out of space. Also diverges by, and we have to say, integral test. So the integral test is our first test that can show both convergence or divergence. Remember, the nth term test can only show divergence. So the behavior of both of them are the same. Since the integral diverged, so would the series. So let's look at another example. And certainly, if you really are ambitious, pause the video and try the second one on your own. But if not, that's okay. We'll do it together. So we're going to take a look at this particular series next. And again, I'm making a note. I'm making a note that that series certainly is not. It's not a telescoping series. It's not purely geometric because you're multiplying by this factor of n. So even though there is a little bit of geometric component to it, the fact that you're multiplying it by n, is making that a not purely geometric series. So part of that is increasing while the other part is decreasing. So what I'm going to do is take a look at. I probably didn't have to erase it, but that's okay. Let's get rid of this guy though first. So let's take a look at what if that were a function, right? What if we had f of x, there it is. So f of x was equal to x times e to the negative x squared. So we want to think about that function, and if it helps you to write it as x over e to the x squared, that might help you as well. We want to make sure that are we continuous on this interval? Yes, from 0 to infinity, e to the 0 is only 1. So we definitely know that it's continuous. So I'd say like note. Oh, I hate writing on my tablet, sorry. And I'm wondering, all these glitches that I'm finding on my smartboard, maybe it's just my tablet. That I have this thought here because I had to write a lot of notes on my tablet last year during the pandemic. Okay, so note. Sorry, a little aside there. F of x is continuous. F of x is positive. Right? We'll never get a negative value because our exponential function is positive. And it is decreasing because the denominator, as we go off to infinity, will get bigger faster than the numerator. So f of x is decreasing. So since I know all three of those things are satisfied, I know that I can apply the integral test. So thus, the integral test applies. And remember, the integral test isn't going to tell us what the sum is. It's just going to tell us the behavior. So I'm going to analyze the behavior of the improper integral. So we'll rewrite this as the integral from 0 to infinity of x times e to the negative x squared. And if the behavior of that integral converges, we'll know the series converges. We won't know what it converges to, but we will know it converges. If that integral diverges, then we'll know the series also diverges. So it's going to require another u substitution, not a hard one. So let's let u equal that negative x squared. So the derivative is negative 2x dx. We just have the x dx, so I'll need a negative half du is equal to x dx. So again, I'm sort of going to temporarily ignore the bounds just to get the antiderivative, and that's okay. So it's negative 1/2 e to the u du. Which is its own antiderivative. So we get, sorry, erase that there, negative 1/2 e to the u. And let's go ahead and put u, which was negative x squared, e to the negative x squared. And we'll evaluate the bounds from 0 to b. And remember, then we make it improper, so it's the limit as b goes off to infinity. So this is what I have to analyze. So limit as b goes to infinity. Let's see. So I'd rather have that e to the negative x squared in the denominator. So it's negative 1 over 2 e to the x squared when evaluated from 0 to b. So one more time, right? Why not? Limit as b approaches infinity of negative 1 over 2e to the b squared minus, we have the negative 1/2. I just put the negative up there, but there should definitely be two negatives, e to the 0. Now, as b goes off to infinity, our bottom is exponentially getting large, but it's in the bottom. So we get a big fat 0 plus basically 1/2. So, which is a finite value. It's 1/2. So the integral value of this is 1/2. Now, that's not what the summation equals. It would be very clear. All that tells me is that because the integral converged to a finite value, so will the series that we use to represent, the integral represented. So I have to make sure that I'm aware of that. Let's go ahead and make our conclusion. So I could say, thus, by the integral test, because we already satisfied the conditions, and you need to write that, by the integral test. Oops, test. Try down here. Oh my goodness. By the integral test. There we go. How messy. Since the integral of f of so f sub n converges, then the series a sub n also converges. And again, the integral test matches behavior. It doesn't say that, oh, this is the sum. No, it's not. It just says because the integral converged, the series will converge too. Now, the natural or the next question is, well, how close are those values? Because if the terms are getting really small on the integral, and the integral represents area under the curve, and you can see where I'm going with this, will that give us an approximation? And the answer is yes, it will give us an approximation. However, it may not be a great approximation, and that's where the integral error test is going to come in. That's what we're going to talk about in tomorrow's class. So right now, this first video is just basically finding integrals that are meeting three conditions, or I should say series that meet three conditions. They have to be positive, they have to be continuous, and they have to have decreasing behavior. If those three things are met, then the integral that represents it and the series will behave the same. They will either both converge or both diverge. So hopefully that gives you at least a start on this topic for the integral test. Next video, we'll look at a p-series test that will help us as well. Okay, so then this video really just going to focus on the p-series test. And we kind of, in class we've really kind of talked about this a little bit. Right? We kind of really set this up because we're really focusing on how fast is the denominator um, increasing, or like how fast are the terms going to zero. And we already know that the harmonic series, which is example, like if I'm at example 6 here, if I look at that very first one, I already know that this one right here is just the harmonic series. This will definitely diverge. And notice I can't use the nth term test because the limit as n goes to infinity, right? If I just look at the nth term, the limit as n goes to infinity of 1 over n is still equal to 0. The terms are getting smaller. We already know that. They're just not getting small enough fast enough. And so I know that diverges. And but I want to formally come up with that with a test, and that's what we're going to do with this p-series test. Now 1 over root n, right? So that's still the limit as n goes to infinity is still going to 0 of 1 over root n. It's still 0, so the nth term test is inconclusive. But if if 1 over n is not going to get small enough fast enough, then certainly 1 over root n will get there even slower, right? So it's still going to diverge. It like diverges worsely. I don't know if that's a word or not, but yeah, it just takes a lot longer to get there, but it's still going to diverge. And again, it's not the harmonic series. It's going to be something else. That's what this p series is going to talk about. Now, in the warm up, we had quadratic in the denominator, and those terms did get small enough, fast enough. So certainly things that are cubic would as well. But I don't, again, I don't really know what the sum is. It's not a partial fraction. I don't know how to find it. But we can look at the behavior, and that's really where this p-series test comes in. So to answer the question, like which ones converge, only 3. Now, I don't really have a very formal way to say that just yet until we get down here to this p-series test. So, and it's called a p-series because of a power series. Like, what is your power? So if it's written in this format, where you have something to to a power, it will converge as long as your p is greater than 1. And this was even brought up in class. Like it's okay if it's like even if it's like 1 over n to the 1.00000000000. Get my point? 0, 0, 1 power. That's okay because it's still strictly greater than 1. It'll converge. But if it's anything that's less than or equal to 1, and obviously it has to be positive, otherwise, if it's negative, then it's easily divergent because it becomes a normal exponent, then we can say it diverges. And that's the p-series test. So here's how you could use the p-series test to determine, does it converge or does it diverge? And again, it doesn't tell us what the sum is. It just tells us the behavior. And so when it says determine the convergence divergence of a series, we're really looking at the behavior of that series. Okay. That's an R, I promise you. Okay. So we look at this. So 1 over n times the cube root of n. Well, I would probably want to write this as just a power. So n equals 1 to infinity. That's 1 over, well, that's the 1/3 power times 1. So that's really n to the 4/3 power. So once I've established that that's greater than 1, I can say the series converges by p-series test. So I would say series, and you could just generically say the series a sub n converges. Now we don't know what it converges to, but we just know the behavior converges by p-series test. And then you have to have some kind of like rationale or like justification. How'd you know? Because, right, your p is equal to 4/3, which is greater than 1. So that's a perfect statement. The series converges by the p-series test because your power, is greater than 1. It's 4/3. Okay. So here we can rewrite this, since this is the 1/5 power and this is just the first power. If I rewrite that as just 1 power, n equals 1, sorry, so messy, to infinity. of 1 over n to the 4/5 power, like that. So now I can use the p-series test to tell it diverges. So I could say my series a sub n diverges by p-series test because your p-value is equal to 4/5, which is less than 1. I'm gonna try that one more time. Yeah, I'm starting to think more and more that maybe it's not the smartboard that glitches. Maybe it's my actual device. Now, again, I don't really have to tell you. I don't really have to say that. Oh, it's greater than 0, because think about it. In this format, right? If you had 1 over n to the p, and you chose p to be -2, so now all of a sudden, you really have n squared, right? If you're choosing p to be -2, well, okay, then let's talk about that series. Well, of course, it's going to diverge because the terms are getting bigger, right? So it's kind of like a moot point. So we just say your p-value is less than 1, and therefore it's not decreasing fast enough. It diverges by the p-series test. So yeah, the p-series test is nice and easy. However, and maybe the caveat is that rarely will it just be a p-series. Like it might be something that's like a p-series. And so then we'll have other tests that we can use, kind of give you a foreshadow. There'll be a comparison test or a limit comparison test. But for now, for this section, we're just looking at a good way to, I guess, formally say the harmonic series diverges, and things that behave slower than the harmonic series will also diverge. It also tells me that when I'm dealing with partial fractions, if it doesn't ask me to find the sum and it just asks me to show does it converge or diverge, I have a way to get there much quicker without having to do the algebra.